Formula One racing machines epitomize pinnacle engineering, striving for peak speed, power, and agility. Yet, amid this pursuit, they grapple with a formidable adversary: overheating. The imperative of maintaining optimal temperature during a race cannot be overstated. Excessive heat not only jeopardizes performance but also poses a serious threat of irreparable damage to the vehicle. In this exploration, we delve into the intricate science and engineering solutions employed to safeguard Formula One cars from overheating. To grasp the mechanisms of cooling, it's vital to first discern the factors precipitating overheating. Friction and velocity emerge as primary instigators, generating substantial heat as the vehicles hurtle forward. Herein lies the role of cooling systems. Air and liquid cooling stand as the two principal methodologies in Formula One. Air cooling, though lighter, exhibits lower efficiency, whereas liquid cooling, albeit heavier, proves more effective. In this realm, the challenge lies in crafting lightweight, aerodynamic vehicles, leaving scant room for the essential cooling apparatus. High-performance engines churn out prodigious heat, necessitating effective dissipation to avert damage to critical components. Chief among the culprits behind Formula One overheating is the ambient temperature. Racing cars contend with a broad temperature spectrum, from frigid conditions to blistering heat. Elevated ambient temperatures intensify the cooling system's struggle to dispel engine-generated heat. Additionally, the velocity at which these cars operate exacerbates the heat conundrum. Accelerated speeds translate to heightened heat production. Engineers face the formidable task of designing cooling mechanisms capable of matching the heat onslaught at top speeds. To combat overheating, Formula One deploys sophisticated cooling systems that meticulously regulate temperature and airflow, ensuring peak performance even under extreme conditions. The cooling techniques employed are intricate and multifaceted, leveraging technologies such as heat exchangers and radiators to whisk heat away from crucial vehicle components. The cooling system comprises various elements, including the radiator, water pump, thermostat, and fans. The radiator dissipates engine-generated heat, while the water pump circulates coolant through the engine and radiator. Additionally, the thermostat modulates coolant flow to maintain consistent temperature, while fans aid in radiator cooling by inducing airflow. Aerodynamic designs of the cars play a pivotal role, optimizing airflow to curtail heat buildup. Recent innovations include active suspension systems capable of adjusting ride height to alter airflow, thereby mitigating heat accumulation. In the event of overheating, prompt action is imperative to avert catastrophic damage. Initial measures involve reducing car speed. Slower speeds equate to diminished heat generation, affording the cooling system a respite. Adjusting the fuel mixture to curtail engine heat production presents another viable strategy. Should these measures prove inadequate, more drastic interventions may be necessary, such as replacing cooling system components or installing additional heat shields. In extreme cases, engine replacement may be warranted to forestall further damage. It's noteworthy that cooling lubricants play a pivotal role in temperature regulation, absorbing heat to maintain optimal operating conditions. Rigorous maintenance protocols ensure each component operates within prescribed temperature thresholds. Despite strides in cooling technology, teams grapple with the challenge of reconciling stringent regulations and weight constraints with the imperative of efficient cooling. Nevertheless, relentless technological advancements continue to expand the realm of possibilities, with teams perpetually innovating and exploring novel cooling methodologies. Unchecked overheating can precipitate perilous malfunctions, potentially disrupting races or prematurely terminating driver participation. Engine failure ranks among the most prevalent malfunctions. Overheating can warp or melt engine components, culminating in catastrophic seizure. Moreover, overheating can inflict collateral damage on surrounding systems, including transmission and suspension. Elevated temperatures cause metal components to expand, leading to misalignment and other detrimental effects. Overheating exacts a toll on Formula One performance, underscoring the imperative of swift intervention. Effective cooling systems emerge as linchpins of success in the sport, testament to the ingenuity and expertise of the involved teams. As Formula One evolves, anticipations run high for further innovations in cooling technology, propelling the sport to unprecedented heights. Leveraging advanced technology and upgrading cooling systems holds the key to more effectively managing overheating challenges. With meticulous measures and meticulously designed cooling apparatus, drivers can continue to push performance boundaries without succumbing to overheating. Every part of a racing car, from the engine to the electronics, requires effective cooling. While the engine is a focal point, other crucial components like the hybrid system, gearbox, and electronics also demand attention. In the past, cooling systems were simpler, but with modern power units, complexities have increased. Despite reduced heat output from the engine, cooling demands have risen due to hybrid systems and turbos. Coolants, a mix of water and glycol, are pressurized to raise boiling points, allowing engines to run hotter and reduce radiator sizes. Oil, circulated under pressure, aids in engine cooling and lubrication. Post-2014 power units introduced challenges in thermal management, especially for hybrid system components, which run at lower temperatures and require specialized cooling. Gearbox oil coolers are crucial for reliability, and hydraulic fluids need cooling too. Air cooling is used for other systems, but directing airflow efficiently within the tight confines of an F1 car is a design challenge. Electronic components, like ECUs and sensors, require significant cooling. Teams even use airflow to cool brake temperature sensors. With regards to the powertrain, thermal management is a primary means to achieve reliability. When temperatures rise even by a quite small amount, power from the engine will be reduced from the hotter air temperatures, but more critically the reliability suffers. Materials are pushed closer to their structural limits and aluminium weakens at raised temperatures, affecting the crankcases and gearbox castings. Heat also leads to thermal expansion of the metals. This closes the design tolerances, so parts can seize or loosen depending on the surrounding materials. Oil loses its lubrication effect, with film strength dropping at raised temperatures, again leading to seizing. With electronics, the semiconductors fail with increased temperature, stopping them from working. Clearly, not coping with the expected cooling demands is a surefire way not to finish a race or finish compromised by a loss in performance or failed subsystem. Liquid cooling, utilizing water or oil, is the primary method for cooling the powertrain. It involves circulating the coolant through a heat exchanger, typically referred to as a radiator for water cooling. Oil coolers and charge air coolers, intercoolers, function similarly but cool different fluids. The engine's water cooling system, driven by an impeller pump, accounts for the largest cooling demand. Conversely, oil circulation relies on a gear pump. Charge air cooling, essential for turbocharged engines, is achieved through air-to-air intercoolers or water-to-air intercoolers. While air-to-air intercoolers are simpler and lighter, they require substantial space and compromise aerodynamics. Water-to-air intercoolers, favored by some teams, require a separate water cooling circuit but offer packaging advantages and more consistent cooling. Cooling systems for the energy recovery system, ERS, components, such as the battery and control electronics, are separate from the engine cooling. They often necessitate multiple cooling circuits and intricate plumbing. Gearboxes and hydraulic systems have their own oil coolers and pressure pumps. Designing the intricate plumbing system is crucial, ensuring efficient heat exchange and proper installation. Components like preheater and bleed pipes are integrated into the system, and connectors from suppliers like Wiggins and Staubli ensure reliability. Piping materials vary based on application, with larger bore pipes in aluminum or carbon fiber and smaller bore pipes in aluminum or titanium. Motorsport-specific connectors are used for sealing, ensuring durability and performance. And that wraps up our exploration of how Formula One cars beat the heat. If you enjoyed this video, don't forget to like, share, and subscribe for more content on the science behind motorsports. Until next time, stay cool and drive fast. And see you on the next video.